Yeah, it's our pleasure to be able to have like Ruslan to be here in our seminar to share about his work. He'll be telling us how to use the kernel bandwidth to improve the generalizations of quantum kernel models. And Ruslan, you can start the presentation. The floor is yours.
Thank you very much. Thank you for the introduction, and thank you for having me. It's always nice to give talk at a new institution. I don't think I've had the privilege of ever talking here before. So I'm going to talk about some of our now not so recent work. I think this is coming up on the anniversary of this paper, but there's still, I think, a lot of techniques that are of interest to the community. This is joint work with Abdul, who's now at Flatiron Institute here in New York, Evan, still at University of Waterloo, Chingiz at Harvard, and Stefan, now division director at Berkeley Lab. All amazing people, by the way. Highly recommend working with them if you have a chance. Okay, so I'm going to start sort of from the basics and work our way towards our result. So to motivate our setting a little bit, I'm going to start from the very back and talk about the sort of common way people do machine learning with quantum computers, which is you have some quantum circuit that somehow embeds your classical data point, denoted here x, into a quantum state using some parameterized unitary. And then you have some trainable parameters and use a layer of circuit with trainable parameters, which you optimize to minimize some loss function. So mathematically, if you write your data embedding as a rho of x, then the thing that you're optimizing for, your loss, can be written as just the value of observable parameterized by theta on this state, which is simply, as you may notice, an inner product in the space of density matrices. So the output of your quantum model is linear in feature space, which from ML 101 tells you that your model is kernel method. So a large class of models of this shape can be viewed as kernel methods. Of course, some caveats apply. So not all trainable circuits, first of all, not all models are like that. So for example, a common technique is to repeat these multiple times. This is so-called data reuploading circuits. And in general, the fact that you're training parameters introduces inductive bias that in general behaves in highly non-trivial ways. I recommend the recent paper from a member of our group, Shavanik Chakrabarty, on the behavior of over-parameterized quantum neural networks and the way in which the training dynamics of those quantum neural networks diverge significantly from the way classical over-parameterized neural networks behave. So this is an important caveat to the sort of perspective that I'm going to take. But the perspective I'm going to take is that all the things we care about is the embedding itself. So we're going to view our model as simply a kernel method, and we're going to only look at the inner product between our embeddings, and then the optimal spreading hyperplane will be found in the classical computer by solving a convex optimization problem. As a standard kernel perspective. I apologize, just 1 second. Okay, thank you for bearing with me. Okay, so now why would that be an interesting thing to do? Why would we want to embed our classical data points into the space of quantum states? Well, coming back to classical setting, and classically, kernel methods are so powerful because being able to study the data in feature space often makes the data easier to analyze. The same idea applies classically, quantumly. We are hoping that by lifting our data into this exponentially sized quantum space, we hope to make the data easier to process. Ideally, in this binary classification case, make the data linearly separable. And the power of quantum kernel methods now comes from being able to process the data using exponentially sized Hilbert space and performing computations that are hard classically, even for size attainable and currently available quantum hardware. So for example, you can imagine a sort of a cartoon example of this, where your embedding is simply you computing the discrete log and you're embedding into 1D. So then you can learn in scale quotes discrete log function. That's an example of how you can use the ability of quantum computers to perform classically hard computation, in this case, Shor's algorithm, to make the data easier to analyze. Now, unfortunately, if you do this straightforwardly, if you take your classical data and you try to embed it into quantum states and perform some sort of learning on the results, you will run into two rather straightforward challenges. So first, note that an n-qubit quantum state is a point in a to the power of n-dimensional space. So if you have, simply geometrically, if you randomly pick points in this on this to the power of n-dimensional in this space, we can view it sort of as a unit sphere, even though geometrically it's not quite correct to view it that way, but it gives us the right intuition. If you pick random points on this high dimensional object, the inner product between them is going to be exponentially small. So your kernel values are going to vanish exponentially. So you would need, for example, exponentially many samples to compute those kernel values. Now, a second and a dual version of this is that the value of a nice function, let's say some Lipschitz continuous function from concentration of measure, is going to be doubly exponentially close to the mean value over all sphere. This is the so-called vanishing gradient phenomenon. The consequence of this, of both of these effects, is that you're going to need exponentially many samples to learn, either from having to estimate your kernel values with exponential precision, or having to estimate your gradients with exponential precision. Now, classically, this is not an issue because the cost of storing and manipulating a number up to log of 1 over epsilon precision, up to 1 over epsilon precision is log 1 over epsilon. But quantumly, our cost of doing so is 1 over epsilon. So what can we do with this observation? How can we avoid this issue of exponentially exploding overhead of learning? Another wrinkle in this picture, in addition to this issue of vanishing kernel values or vanishing gradients, is that even if we could estimate them with arbitrary precision, which we do for this plot, the kernel matrix is going to approach identity exponentially. It's going to become diagonally dominant and then, further worse. And as a result, your model is going to overfit. So if you look at your prediction accuracy and you grow number of qubits using this naive construction where you just use IQP feature map, which is based on instantaneous quantum polynomial circuits, your prediction accuracy drops off to random guess at about 19 qubits. This observation has been made many times before. This is just reproducing this plot from this Power of Data and Quantum Machine Learning, very famous paper. And note another thing worth noting here, that this stuff happens not just asymptotically. This happens very, very fast. So here, already at 15 qubits, you're doing pretty much random guess. Now we can further drill down into this phenomenon to really understand what is happening here. And to do that, let's consider an even more cartoonish example. Let's consider that our kernel, which is just Rx rotation on each qubit. Our feature map is just Rx rotation on each qubit, which means the kernel is just cosine kernel factorizes over qubits. And consider our data to be 0 and pi, strings of 0 and pi. And let's say we learn some function. It doesn't really matter what function we learn, but we're going to learn cosine of the last bit, which in this case it's either plus or minus 1. So we're just learning the parity of the last bit. Now, this is a classically trivial problem. You could easily see like a linear regression is going to be able to learn this problem. However, our quantum feature map takes each one of these data points into a computational basis state. So as a result, all of our data points are orthogonal to each other, and our kernel, as easy to check, is a delta function. And if your kernel is a delta function, you're going to need exponential number of training samples to generalize. Essentially, you will have to have seen all the data to generalize. So you will have to have seen all strings of 0 and pi, of which there's exponentially many. We're going to come back to this cartoon example in a minute. But first, let's remark that these problems are very well known in classical literature. Classically, we often learn in high-dimensional spaces, and things are working out just fine, even in kernel case, without the additional benefit of the dynamics of gradient descent, which is another way the problem of high dimensionality is overcome classically. As an example, let's consider the radial basis function kernel. So this kernel, its feature space, is infinite dimensional. So of course, if you just imagine you were embedding randomly into the feature space of this kernel, you're going to have this issue of, you could call it overlap catastrophe, where any two embeddings are going to be orthogonal to each other or near orthogonal to each other. So how come kernel models with using RBF kernels succeed? And the answer, of course, you already know it. The answer is that because there's this hyperparameter gamma, which controls the expressiveness of your model. So depending how you tune this hyperparameter, it biases you either towards wigglier decision functions or towards smoother decision functions. This hyperparameter is called bandwidth. So what we're going to do is we're going to start by taking our toy example and introducing an analogous bandwidth hyperparameter, which now is going to be equivalent to the rescaling of the data points. So we're introducing this hyperparameter C, which we're going to consider analogous to the bandwidth in the classical RBF kernel. I'm sorry. Now what happens is that the kernel is no longer a delta function, and our model now generalizes. Now, on the right, we're plotting the generalization error versus number of training data points for varying values of bandwidth. And you can observe two things. So one is, now if we allow the bandwidth to vary, so bandwidth 1.0 corresponds to the original setting. If we allow the bandwidth to vary, then the proof of generalization improves and the generalization error drops dramatically as we increase number of data points to not even that large of a number. So to the 6 is 64, I think. And remember, we're learning in 2 to the power of 50 dimensional space. So our model now generalizes well. Another feature you can notice is that lower value of bandwidth gives you better generalization. So what's happening here? And this is going to help us understand the mechanism by which the bandwidth enables generalization in this case. So if we plot the spectrum of our kernel, so we're looking on the x-axis eigenvalue index, and the y-axis the value of the eigenvalue, and lines are drawn to guide the I. There's nothing in between the first and the second eigenvalue. We see that the lower the value of the bandwidth, the larger is the first eigenvalue. So jumping ahead a little bit, since the first eigenfunction of our kernel is constant, so all we want is a linear model, so a constant eigenfunction is good enough for us. Larger first eigenvalue gives us better generalization. Now, why is that? So to understand this mechanism better, we turn to the framework of task model alignment. And I'm not going to give, and the task model alignment is a non-rigorous framework, which gives you explicit formulas for generalization error. It's based on some ideas from statistical physics. I don't want to bore you with too many formulas, but I want to give you a rough flavor of the way it allows you to characterize the generalization of your model. To do that, consider the decomposition of the target function that you want to learn, f bar, in the eigenbases of the kernel. So take all the eigenfunctions of the kernel. If your kernel is finite dimensional, this is eigenvectors of your kernel matrix. They approximate the eigenfunction of your kernel. And so this is the thing you can do numerically. And then consider the cumulative power that your target function has on the first L modes. And so essentially, to guarantee generalization, we want to learn enough modes so that the cumulative power is close to 1. Now the cost, how do we learn these modes? the cost of learning each mode depends on the corresponding eigenvalue. So the smaller the eigenvalue, the more data we need to learn that mode. So if the spectrum is flat, or all eigenvalues are exponentially small, then we're going to need exponential number of samples to learn each mode, even the exponential number, even to learn the first mode. Now, in the quantum case, for the toy example of the kernel that I gave you earlier, we derive analytically the eigenvalues and eigenfunctions of the kernel. This we can do because the kernel on n qubits is finite dimensional object. It's just a matrix. And we obtain explicit formulas for the generalization error. I'm not going to put them here on this slide. I'm just going to give you the high-level picture. So again, like I said earlier, remember, we want to learn enough modes so the cumulative power is close to 1. If all the power of our target is on the first eigenfunction, we only need to learn the first eigenmode. So all we care is to make the first eigenvalue as large as possible. That'll make our learning easier. And that's why in this particular mod problem, this toy trivial problem of learning the parity of the last bit, we succeed. Essentially, the smaller the bandwidth, the more we succeed. And because of the triviality problem, we get good generalization with 50 data points. Now, in general, this is not going to be the case. So to take a look at how these dynamics play out in a case of we have the same kernel, same toy quantum kernel, but a different target function. So here we're learning this target function, which is slightly more complicated. Here we have dynamics that are more typical. So first we plot the spectrum, so the eigenvalue versus the eigenvalue index, and we see that the smaller the value of the bandwidth, the less flat the kernel spectrum is. So we go from completely flat at eigenvalue at bandwidth parameter 1 to the least flat at bandwidth parameter 10 to the minus 2. However, the cumulative power is maximized not at the smallest bandwidth, but at some intermediate value of the bandwidth parameter. And lo and behold, the green line, which is the optimal maximum test model alignment, corresponds to the lowest generalization error. So our theory predicts the performance well. Now I can take the same techniques and apply them to the to other quantum feature maps proposed in the literature. So now these are quantum feature maps that are not analytically solvable. I cannot solve them in closed form, and they're conjectured to be hard to classically simulate. And what we're going to do is we're going to analogously introduce a hyperparameter to them, which we will call the bandwidth of quantum kernels, which in this case corresponds, in case of Hamiltonian evolution feature map, corresponds to the time with how long we evolve the system with Heisenberg model. And in case of IQP, it's this hyperparameter lambda here. In both cases, it's equivalent to the rescaling of the data input. So the intuitive behavior we observe on the toy example, from analytical results on which we learn this intuition, persist for when we look at IQP kernel applied to fashion this data set. So even though our both feature map and the data set are far from outside from theoretical assumptions, for example, our derivations rely on the data factorizing over qubits, which of FMNIST, of course, does not, as the data are pixels. We see the same behavior. So optimizing the bandwidth gives less flat spectrum and higher target model alignment. And of course, it gives better performance. We can come back to this example that we looked at in the beginning, where we took the results from this power of data paper. Now we tune the bandwidth and we obtain prediction accuracy that is close to classical state-of-the-art result they report in that paper. Note also that both on the previous slide and on this slide, as we increase number of qubits, which is here data point dimension is just equal to number of qubits, we do not see catastrophic drop-off in model performance. Instead, our prediction accuracy continues to grow as more features are available to the model. This is in sharp contrast to the previous results showing that high dimensionality of the features of the quantum Hilbert space prevents learning. To sum up, controlling the inductive bias of the quantum kernel model is a prerequisite for generalization. Bandwidth is one technique, but more techniques are needed. And this is by no means the final word on that. We analyze the large qubit limit in this paper, and we provide explicit formulas for generalization of a quantum model that can be solved in closed form. We use this analytical formula to obtain intuition and apply it to real world, more realistic models and more realistic data. We show on those real models and on the real standard benchmarks that optimizing bandwidth takes the model from not generalizable. In case of the toy kernel, we can prove that it cannot generalize, to being able to generalize for well-aligned targets. And on the standard benchmarks, we observe performance compared to a state-of-the-art. You can check out our papers for more details. As a final, almost mandatory note, our team is growing. We're always looking for talented students for summer internships for 2024. Our applications will open sometime in the fall, and we're hiring for full-time roles. Don't hesitate to reach out. It's an amazing team, and it's a privilege to be working in it. Thank you so much. I think that's all from me.
Yeah, thanks, Ruslan, for the very intuitive and interesting talk. For the audience, like if you have questions, you can either type in the chat, I could like read it out, or you can just like unmute yourself and ask the question. So I guess while people is thinking of what question to ask, I could start off with some questions. So over here, you kind of like making use of the task model alignment, right? Is it hard to evaluate this quantity? Because like it's quite because over here you're basically trying to decompose your target function in terms of the eigenfunctions of written them in terms of eigenfunctions of the kernels, right? And then with this community powers like hard to evaluate because if it's simple to evaluate, that means like for each of the model, then we can try to calculate this quantity and quantify how well our model will be able to learn the models, right? The target function.
Yeah, that's a great question. And so we released the code for the. I wasn't the one doing this numerics. Abdul did the numerics, so the code is public. I'm pretty sure. If you can find it, shoot me an email. I can point you to it.
Okay.
But the short of it is that it's written in sort of the scary way, but really this is a sum because we're in finite dimensions, right? And so you have this. I think that's true.
Yeah, because like normally we
know
what is the eigenfunctions, right? We have to do the decompositions of the kernel.
No, but this is the easy part. Oh. So this it is approximated in finite dimensions, infinite number of data points. This is approximated by the eigenvectors of your kernel matrix.
Right.
So if you just do decomposition of your kernel matrix, you get eigenvalues and eigenvectors. So eigenvalues are the values that they're going to use for the let me see. I don't have this formula here, but eigenvalues you plug in for how much data you need to learn a mode, and then your eigenmodes are just eigenvectors. And then this decomposition you could do numerically. So that's the beauty of task model alignment, and that's why it was so powerful when Abdul and Chingiz came up with it for classical wide neural networks, because you can numerically do it for example, neural tangent kernel, because you can just take the kernel matrix, do the diagonalize it, and you'll get the eigenfunctions and eigenvalues, and then you can compute these quantities and use them to predict the generalization.
Right. Yeah, it is really very interesting for me because currently I'm just like dealing with the eigenvalues of the kernels, and I haven't like really okay, this is my kind of like on my plan, but I haven't like find a way to kind of study the eigenfunctions of the problem that we want to study, or like or the kernel that we want. Because like at the beginning of your talk, basically you kind of like introduce that okay, the Kernel neural network is basically a submodel of like quantum kernel methods, right? And then any functions in the RKSS, like, sorry, I involved some technical terms over here, could be written in terms of the eigenfunction. Any models in this RKSS could be written in terms of the linear combination of the eigenfunction, right? Yeah. So in this case, could we study the quantum neural network using the eigenfunctions of the kernels per se, and then trying to see how powerful it is?
I think yes, but there are big caveats.
Mm-hmm.
So I think what has been coming up in the literature, and that's why I spent maybe a little more time every time I give this talk, I spend more and more time on this caveat,
Mm-hmm.
on this, is that the dynamics of gradient descent impact your generalization. And there's this lovely paper, I think it was from Jan Zeiser's group, but it's late here in New York, so I may be forgetting things, where they come up with explicit examples of where kernel, if you just do the kernel perspective, so if you just do this and find the truly optimal separating hyperplane, you're gonna overfit.
Mm-hmm.
But if you do this and you do gradient descent, you're gonna generalize. And they have these like lovely numerical examples
Right.
of explicit targets with this and explicit data points where this happens. And this is very illustrative because an important thing that, is, I think, at least when I first started looking at this, overlooked, is that really there's a lot of inductive bias that you can hide here. And
yeah, of course. So if I'm not wrong, I will like go this into detail. I remember like for the classical communities, they study the inductive bias that's imposed by the optimization process. They call it like implicit inductive bias, if I'm not wrong. So I think this is kind of like like they are studying this kind of this form of inductive bias in the classical literatures, and yeah, it's kind of interesting to see like how we can port over their results and adapt it to the quantum one.
Yeah, definitely. I'm not an expert on the classical literature, but I think
Yeah. As in, yeah, now I'm just kind of like beginning to look into more the classical one and see like what can we um kind of like learn from the classical literatures and use it to study the quantum kernels. Um yeah, and the other question that I have for you is the spectrum between like projected kernels and the one that you get from the kernel bandwidth. How are they different?
Yeah, so we talk about it in the paper, and
Yeah,
let me remember, I haven't looked at
because
this,
yeah,
but
okay.
the
So for
simpler,
Mhm.
yeah, go
Yeah,
ahead.
no, as because like in that papers, right, what I found is that your um it only considers like one subsystem, but then for projected quantum kernel, you normally consider the sum of the subsystems, right? Right, like in this
Oh, I see.
yeah, how like now like if you consider summation as in like actually this is what I'm studying currently, but I'm just like just trying to see is like what is your opinion on that, because like maybe the sum, as in I found that the sum will have impacts on the eigenvalues, but in your opinions, like how will that affect the generalization abilities?
Yeah, no, you're right, because the sum makes it less trivial. Yeah, because if it's just one subsystem, then you have sort of this terrible picture where only
Yeah.
the first, only the first eigenvalue is high, and everything it's immediately exponentially small. And
Yeah.
even, I mean, Kubler made that point in their paper as well, which is why.
Yeah, just like upper bounded by the integrations of so the trace of the rho square or whatever like that is, right? Yeah.
Yeah, I don't know, but some shouldn't help you too much, because, I mean, you only have a linear number of subsystems.
Mm-hmm.
So it's not like you can overcome exponential vanishing by summing up a linear number of
Yeah, but
things.
what if it combines with the kernel bandwidth techniques, right? As in like kernel bandwidth will help you in some case, and then now like if you have summation, then it could like help you to impose some other inductive bias, right?
I mean, I think that's a great way to look at great thing to look at. I mean, as I sort of try to highlight here, bandwidth is just one technique.
Yeah.
I mean,
Yeah.
in fact, we have a paper numerically showing that just bandwidth alone is not good enough
Mm-hmm.
for advantage. at least
Right.
numerically, that we have strong evidence that it's not good enough. But it can be one technique in the toolbox
Mm-hmm.
of many.
Mm-hmm. Right. Okay. Yeah. I think I will try my best to write a verse, and maybe it's like we can discuss it after my paper come up, because I kind of like study extensively how the summations and the projections will affect the inductive bias of the quantum models, and maybe kind of like be able to generate some discussions and looking forward for those discussions. Yeah. So seems like all those yeah. Yeah, as in, I found like the kernel memory is really an interesting techniques, but then it seems to me that it's quite expensive to evaluate, right? Because like for different kernel bandwidth, you have to run different circuits because you have to do different encodings, right? Do you kind of have a simple or like resource like that technique that is not required that much resource in order to pick which kernel bandwidth that's best for your task? Do you have an idea in mind? Because
Yeah, I think there was I think it's like 1/square root d is the optimal one for the toy kernel. So
yeah,
so I think
so
that's if d is now your number of qubits, I think 1/root d. Again,
okay, yeah,
I might not be remembering correctly.
yes,
It's similar to the paper, the Gaussian initialization of a quantum neural networks. Essentially, if you initialize with n of 0, 1/root d, I think,
but then
you
will
can
this
show that this initialization doesn't give you Barron Plateaus, and it's exactly the same phenomenon, just slightly different math to show it.
will this techniques only apply to a particular ansatz, or it apply to arbitrary ansatz as well?
I think this relies on like this if you're very expressive. Like this gives you I think in case of the QNNs, this gives you a lower bound on your gradients, even if your Haar random, even if your ansatz mixes to Haar with completely random initialization.
Right.
So I think it should work always.
Okay. Then I should look it up.
It may be worth looking.
Yeah.
Maybe worth consider. It can be a good starting point. Generically, I mean, classically, there's no really hard rules. Like even for something as well studied as RBF, and RBF's been beaten to death, right, over decades of research. Even for RBF, there's not a hard and fast rule for setting bandwidth.
Right.
So hyperparameters are just, you're always going to have data dependence, because for any choice, you can construct a counterexample.
Yeah, I completely agree with you. Yeah, I think it would be kind of cool to find a simplified method to evaluate the best kind of bandwidth. Yeah. So okay, it seems like now people are starting getting more attention on using like putting over like more and more result from classical literatures to the quantum one. Like I think the target model alignment is the concept from like classical literatures, right? Yeah. Okay. Okay, I think like there might not be questions from the audience. Currently maybe that just needs some time to digest the information, and maybe they will kind of like drop a message, email to you and ask questions if they want to. And I think I will go through your papers again and to see like if I have any extra questions. And if that's the case, then I will like drop you an email and trying to like discuss further on your work, and especially I'm interested on the like technique that you use, or or others use to analyze the quantum model. Yeah, I think for now we can end seminars, and thanks Ruslan again for spending his time with us to prepare this like interesting talk. Yeah, thanks everyone. See you.
Thank you for having me, and thanks for the questions.